All right, welcome back. In this video, we're going to be talking about continuity. Now, you may have heard about continuous functions in previous course, and I think probably the definition you heard was that a function was continuous if you could draw its graph without lifting your pencil up off the paper. Okay, so in calculus, we're going to have a new definition. And that's going to be that a function is continuous at a particular x value if the limit as x approaches that x value is equal to the value of the function. So let me draw you a little picture here. So suppose the limit of f of x as x approaches c exists, right? Okay, the limit exists. But it is not equal to the value of the function. Okay? That would be discontinuous, right? There's a little hole in the graph, right? If we were going to draw a picture of it, we'd have to draw the left side first, then we'd have to draw the right side after to get that separation where that hole is. Okay? If f of c was undefined, well, that's another place where it's going to have to be discontinuous because there's just no graph there. Okay, but it would be continuous at this spot if we had f of c equal to the value of the limit. Okay, and that's going to be our definition. It's actually a really good definition of continuity. It just depends on our definition of a limit, which in this class is not that robust. Now, in AP Calculus, there's going to be two main types of discontinuity: removable, non-removable. Okay, now hopefully, I think I want you to just really mostly be thinking about what these types of discontinuities look like rather than the, mathematical specification of them. Let me just draw you a picture of a removable discontinuity. Okay? It's a hole in the graph. Okay? And kind of the critical aspect of a removable discontinuity is that the limit of f of x as x approaches c exists, but that limit is not equal to the value of the function at x equals c. But is not equal to the value of f of c. Okay, and we can see that in this case it's not equal because f of c is undefined. But if f of c was defined and it was elsewhere, like, I don't know, right there, that would still be a removable discontinuity because the limit exists, but it's not equal to the value of the function. Okay? Say, oh, you can remember this because it's a removable discontinuity because it looks like an otherwise continuous graph that somebody just went and removed one point from. Okay? And now a non-removable discontinuity is really anything else. Okay? And there are other names for these, elsewhere, but for now we'll just call it non-removable. Okay? There's going to be a jump discontinuity where the function just jumps. We've already seen a couple of these so far in this class. Oh, whoa. Okay, I'm still in my shot. That's a jump discontinuity. It's non-removable because the limit doesn't exist, right? The limit as x approaches this x value, that doesn't exist. Okay. Another one would be a vertical asymptote. Okay, maybe like that. Or even if they were both going up. Okay, the limit as x approaches c of f of x fails to exist, and that's the factor of a non-removable discontinuity. All right, so the first example I want to talk about is just like what x values makes the function discontinuous and what kind of discontinuity are we looking at. So let's just, g of x equals x minus 2 divided by x plus 3. Okay, we know that division by 0, that's definitely a no-no in this class and in most math classes, right? So we're going to say that x equals negative 3 is a place where this function is discontinuous, and because if I actually tried to plug in x equals negative 3, I'd have negative 5 divided by 0. We know that's the location of a vertical asymptote, right? So we're going to say this is a non-removable discontinuity. Okay? If you wanted to be more specific, you could say there's an infinite discontinuity, and that's language that some people use. Okay, but for this class, we just need removable and non-removable. Okay, next, suppose g of x is a piecewise defined function, where g of x is equal to x squared, just as long as x is not equal to 1, but 4 if x is equal to 1. Okay, well, we know how to draw a nice little picture of y equals x squared, right? Parabola, and then on the right side, it's good, except for right here, it's not there at 1. That's what they told us. It's a parabola everywhere except for 1. And then at 1, y equals 4. Okay. x equals 1 is the location of a discontinuity, and it is a removable discontinuity because it's a hole in the graph. Now, if g of x is some kind of rational function that looks like it has redundant factors, then we would factor, cancel, and see what happens, right? See if it can be canceled. I'm going to factor out an x from the top, and I've got an x minus 5 on the bottom, so I'll be able to cancel that. And we know that when we cancel off factors on top and bottom of a rational function, that gives us a hole. So this looks like the graph of y equals x with a hole in the graph where x equals 5. Okay? That's going to be x equals 5 is the location of a discontinuity, and it's a removable discontinuity. Right, now the last function I want to just bring up as an example and remind you about is this type of thing where I have a thing divided by the absolute value of that thing, or the absolute value of a thing divided by the thing without the absolute value. Okay, we need to be aware of what this graph looks like. Okay, so we know that the graph of x divided by the absolute value of x is the one that goes 1 and negative 1. This is going to be very similar, except all the action is going to happen at x equals negative 2. So we know that for x bigger than negative 2, y will equal 1. Maybe I can get a nice straight x-axis. That wasn't the best, but it'll be all right. And then down here, okay, at x equals negative 2, I have a jump discontinuity. Okay, this is non-removable. Next, I've got this example, and this is honestly probably the most typical continuity question from AP Calculus. It's like find the value of k that makes the piecewise defined function continuous. And so, really, okay, over here where it says it's a quadratic for x is less than or equal to 2, maybe I'll kind of draw a sketch of that in red. Okay, it is going to go up a little bit because of, where the vertex is, but that's, very approximate parabola. It does have the filled-in circle because x is less than or equal to 2. Over here, where x is greater than 2, it's some kind of like line with some undetermined slope. And now what we're going to do, we're not going to be doing a vertical translation, but we are working to solve for the value of k so that these things can meet up and we have ourselves a continuous function. That's what we're going to do here. And how we're going to do it is we're going to take the two pieces of the piecewise defined function, set them equal to each other, and make sure they're equal at the x value that they kind of share or would be split apart at. So x to the 2 minus 3x plus 9 needs to equal kx plus 1 where x is equal to 2. Okay, that's going to be important. Okay, I'm going to plug in x equals 2, and I'm going to get 4 minus 6 plus 9 equals 2k plus 1. Okay, so that's looking like 7 minus 1 is 6, equaling 2k. So I'm going to conclude that k is equal to 3. And that's going to make the function continuous at x equals 2. And we know that polynomials are continuous everywhere, so it's going to be continuous at all x, just provided it's continuous at x equals 2, where the pieces. Right, now we've got another type of question that is very similar, but it's going to have 3 pieces, and there's going to be 2 variables that we need to find the values of. Okay, so we're going to end up with 2 equations with our 2 variables, and we're going to have to solve a little system. But overall, what I'm going to do is, where an x value is shared, I'm going to set those 2 pieces equal to each other. So I'm going to say that x minus 4 equals ax plus b with x equals negative 2. And then over here, where they share 1, I'm going to say that ax plus b equal to x plus 2 at x equals 1. Okay, I'm going to kind of reduce these down, and I'm going to end up with 2 equations in a and b, and I'll have a system, and I'll be able to solve it. All right, so plug in negative 2, and I'm going to get negative 6 equals negative 2a plus b. And if I plug in 1, I'll get a plus b equaling 3. Now I'm going to give myself a little more room, bring this on down there. And at this point, it's kind of like up to you. How do you want to solve this system? Do you want to use substitution? You want to use elimination? I don't know. Maybe you're in my linear algebra class and you want to use row reduction. I don't know. I'm just going to copy these, and I'm going to start with negative 2a plus b equals negative 6. And then I'm going to take a plus b equals 3, and I'm going to double it. So I have 2a plus 2b equals positive 6. And then I'm going to add these equations together. Okay, and I'm going to have 3b equals 0, which means that b equals 0. And since a plus b needs to equal 3, I'm going to conclude that a is equal to 3. And those are going to be the values of a and b that make the function continuous for all x. Now let's talk about the intermediate value theorem. Okay, and this is a theorem. This is the first of our existence theorems for AP Calculus, and there's going to be kind of 3 of them that guarantee you the existence of something, just provided some conditions are met. And really important to note that for the intermediate value theorem, it's only valid if f of x is a continuous function. So if f is continuous on a closed interval, and y0 is a number between f of a and f of b, and I'm going to draw you a picture. Right, so here we've got ourselves, a, b, f of a, f of b. With no loss of generality, I'm just going to assume that f of a is less than f of b, but it's not going to change the result at all. You can envision it being the opposite. So say y0 is just some y value in there between f of a and f of b, like we said. What I'm saying is that if I go continuously from one dot to another, I have to cross over this horizontal line. Right? It's not going to be possible for me to cross, or for me to not cross it, especially if it's continuous. Right? If it was discontinuous, maybe it stops and picks back up over there. But if it's continuous, I have no choice. I can put it off for a while, but eventually I'm going to have to cross that. And I will also mention that I'm not going to be proving this theorem in this video because the proof of this theorem requires techniques that are beyond the scope of AP Calculus. In this class, we have to take this theorem as self-evident, right? I think it's like, of course, if it's continuous and I go from that dot to that dot, I have to cross over the line, right? So just, putting that theorem to a little bit of work right here. If f is a continuous function, what is the minimum possible number of x-intercepts on its graph? Okay, I'm going to show you how to do this one 2 different ways. First, I'm going to draw a picture. I'm going to sketch a picture of the graph, right? I'm going to say there's 0, that's 10, and well, negative 2 feels like it might be down here. I don't know, 5 could be like up here, 0, negative 1, a half, this, right? I'm just really saying positive for negative. Okay, and then maybe it's, some kind of function that goes up and then down and then up again. I don't know. Okay. This is a pretty minimal connecting of these 5 dots. Okay, and I'm seeing 1, 2, 3 x-intercepts. So I'm going to say there's at least 3. And that's the whole idea. But it has to do with the fact that this is a continuous function. Okay, what else? Oh, I was going to say, numerically, we could see that on the table by looking for sign changes. Okay, there I'm seeing a sign change, right? Went from negative to positive, but that's the same evidence of that 0 right there. Over here, I'm seeing a 0 on my table. That's really generous, but okay, there's that one. And then here I have another sign change. And that's what's represented over here. So you could do this without sketching a graph, just if you were looking at the table and thinking about it that way. It's just, how are you interpreting these things? Now I might give you a table of values for a function g of x and tell you it's continuous. Okay, that's important to this discussion, otherwise there's not going to be an answer. The question is, what values of b guarantee 2 solutions to g of x equals 1 on the interval 0 to 2? Let me give you a couple seconds to think about that, and then I'm just going to tell you the answer. And then I will draw you some pictures to try to convince you. All right, I hope you have a conjecture, but my answer right here is going to be b is less than 1. Okay? And let me draw you a picture to try to show you what I'm thinking when I'm looking at this. Okay? If we've got 0, 3, and 2, 5, and we're talking about g equals 1, so I'm going to put that on there as well. And 0 up to 2. Okay. If g of 0 is 3 and g of 2 is 5, and we're interested in the solutions, okay, g is a continuous function, so I don't know, maybe it looks like that. Solutions to the equation g of x equals 1 is going to be intersections between the graph of g and this horizontal line right here. Okay. Well, this is 1, and g of 1 was, I don't know, bigger than 5. That's not going to guarantee 2 solutions to g of x equals 1. That guarantees nothing, right? I didn't see any. But if g of 1 is anything less than 1, I'm guaranteeing that there will be a crossing as I go down underneath y equals 1 to get to, say, g of 1 equals a half. To get down there, and then I'm going to cross it in and go back. Or maybe it's negative, and I'm going to have to go down here. Either way, if g of 1 is negative, that's going to guarantee 2 solutions to g of x equals 1, provided that g is continuous. Okay? If b was equal to 1, we could have a situation where we were bouncing. Okay? And if g of x was greater than 1, we could have a situation where we didn't even have any solutions. Okay, so less than 1 is what guarantees 2 solutions. Now I'm going to wrap up by talking to you a little bit about average rate of change. Average rate of change is the type of thing that we're going to be very interested in the next lesson, once we start really doing our good old-fashioned like calculus stuff, right? Rates of change, slopes of lines, slopes of curves, right? This is really very calculus. But we got to start by talking about an average rate of change. But the good news is, you've seen this before, a long time ago. Average rate of change, that's just a fancy word for rise over run. Okay? Now, we're not going to call it y2 minus y1 over x2 minus x1. We're going to call it f of b minus f of a, well, that's weird, over b minus a. Okay? And I feel like I had something else to say about this. I'm just going to really emphasize that this is rise over run. And on the graph of y equals f of x, the average rate of change of f on a to b represents the slope of the secant line. So I'm just going to write that in there, slope of the secant line. But maybe you're like, I don't think I know what a secant line is, and that would be understandable. Okay, you know about secant of an angle, it's 1 over cosine of that angle. And there is a connection between, using that same word for two different things. But I needed to show you what the secant line is, right? If I've got, thanks, don't shut up. If I've got some kind of function like that, the secant line is the that connects the 2 points, okay, 2 distinct different points on the graph, okay? So this is our secant line. Later on, we'll be interested in like a tangent line, which, would be something like that, where it only touches in the one spot, but that's for the next video, okay? We're talking about the secant today, okay? And the units of a rate of change or of a slope or of, later on we'll call it a derivative, okay? So the units of a rate of change or of a slope is going to be units of the dependent variable, which is oftentimes y or f or whatever, divided by units of x or whatever the independent variable is. So, for example, water is pumped into a tank at a rate of R of t liters per hour, where t is measured in hours. What is the average rate of change of R over the closed time interval 1 to 3 hours? indicate units of measure. Okay, well, we have a formula, right? We know that it's f of b minus f of a over b minus a, so in this case it's going to be r of 3 minus r of 1 divided by 3 minus 1. Okay, and the units are going to be units of r divided by units of t. Right? This is going to be 950 minus 1190 divided by 2. Units of r are liters per hour. Per hour, because units of t is also in hours. Okay. Now, if you wanted to say that this quantity was equal to negative 120 liters per hour, that's fine, but remember that we can stop with this and be, perfectly safe on the free response section of any of the quizzes or tests in this class. Now, the last example I've got for you is another average rate of change problem, but this is really just a kind of a contrived way for me to get you to practice some other things. Oh, this is not going to work. I need that to be sine of pi x. Okay, now it's ready to go. This will be a good example now. Okay, we know the average rate of change of g on 1/2 to 3/2 is going to be g of 3/2 minus g of 1/2 divided by 3/2 minus 1/2. Okay. Well, that's going to be, we're going to end up dividing by 1, so that's something nice. So it's going to end up being 4 to the 3/2 times the sine of 3 pi over 2 minus 4 to the 1/2 times the sine of pi over 2, all divided by 1. Okay. Well, I know how to take 4 to the 3/2. You start by taking 4 to the 1/2 power, that's the square root of 4, that's 2. Take that to the 3rd power, so that's 8. So that's 8. Sine of 3 pi over 2 is negative 1. Minus 4 to the 1/2 power is 2. And sine of pi over 2 is going to be 1. And then I'll divide by 1, and I'll get negative 8 minus 2 more is negative 10. Okay, so that's the average rate of change of g over the closed interval 1/2 to 3/2. Okay,